Somewhere out in the darkness of space, there is a point where the laws of physics, as you understand them, simply stop making sense. A place where light itself cannot escape, where time and space trade places, and where the very concept of a straight line loses all meaning. Now imagine that you, personally, are falling toward it, drifting closer and closer to a black hole with absolutely no way to stop or turn back. This is not just a terrifying idea. It is one of the strangest and most scientifically fascinating scenarios in the entire universe, and what would actually happen to you is far weirder than most people realize. Start with the basics of what you are even approaching. A black hole forms when a massive star runs out of fuel and collapses in on itself so completely that its gravity becomes powerful enough to trap even light. The boundary around this collapsed object is called the event horizon, and it marks the point of no return. Cross that line, and no signal, no light, and no information of any kind can ever travel back out to the rest of the universe. Beyond the event horizon lies the Singularity, an infinitely dense point where, according to current physics, space and time, as you know them, completely break down. As you begin your fall toward a black hole, the first thing you would notice depends entirely on its size, and this detail changes everything about your fate. If you were falling toward a relatively small, stellar mass black hole, the kind formed from a collapsed star, you would be in serious trouble long before you ever reached the event horizon. These smaller black holes have an incredibly steep gravitational gradient, meaning the difference in gravitational pull between your head and your feet would become extreme within just a few hundred miles of the black hole. This difference in force is called tidal stretching, and it would begin pulling your body apart, stretching you into a long, thin strand of matter, a process astrophysicists have nicknamed spaghettification. You would be stretched vertically, while simultaneously being compressed from the sides, and long before you crossed the event horizon, you would already be torn apart at the atomic level. But here is where it gets genuinely strange. If you were instead falling toward a supermassive black hole, the kind found at the centers of galaxies, including our own Milky Way, the outcome would be completely different. Supermassive black holes are millions or even billions of times more massive than the Sun, and because of how gravity scales with size, their gravitational gradient near the event horizon is actually much gentler than that of a small black hole. This means you could potentially cross the event horizon of a supermassive black hole without being torn apart immediately, feeling essentially normal gravity as you pass the point of no return, completely unaware in that moment that you had just left the observable universe forever. Now imagine you are an outside observer watching a friend fall into this supermassive black hole while you remain safely at a distance. From your perspective, something bizarre would happen. As your friend approached the event horizon, gravity would begin to warp time itself, a real and measurable effect predicted by Einstein's theory of general relativity. Time would appear to slow down for your friend as they got closer and closer to the horizon. From where you are standing, you would never actually see them cross it. Instead, you would watch their image get slower and slower, more and more redshifted, essentially freezing and fading into darkness right at the boundary, as if time simply stopped for them at that exact point. Even though from their own perspective, they would cross the horizon in a completely normal, unremarkable instant and continue falling. This mismatch between what you would see from outside and what your friend would experience from inside is one of the most mind-bending consequences of black hole physics. To you, it would look like your friend was frozen forever at the edge, growing dimmer and dimmer as their light took longer and longer to escape the increasingly warped space around them, eventually becoming undetectable. To your friend, none of that delay would exist. They would simply fall, cross the horizon, and continue toward the center, experiencing time normally the entire way, completely unaware that from the outside universe's perspective, they appeared to be suspended in time forever. Once past the event horizon, you would be in a region of space where the very structure of reality shifts dramatically. Inside a black hole, space and time effectively swap roles in a strange mathematical sense. Falling toward the singularity would no longer be a choice, or even a direction you could resist. It would become as inevitable as moving forward through time is for you right now. Every possible path, every possible direction you could try to move would lead only toward the singularity, in the same way that every moment of your life, right now, only moves forward, never backward, no matter what you do. As you continued falling toward the singularity itself, current physics runs into a wall. According to general relativity, the singularity is a point of infinite density, where gravity becomes infinitely strong, and the equations that describe the universe simply stop producing meaningful answers. Many physicists believe this signals that general relativity alone cannot fully describe what happens at this scale, and that a complete theory of quantum gravity, something scientists are still searching for, would be needed to accurately describe what truly exists at the very center of a black hole. In other words, nobody actually knows what happens to you at that final point, because the physics you would need to describe it has not yet been discovered. There has been a lot of popular speculation about black holes acting as gateways to other universes, other points in time, or even other locations within our own universe through theoretical structures called wormholes. Some mathematical solutions to the equations of general relativity do technically allow for these kinds of connections, particularly in a hypothetical, idealized version of a black hole called an eternal black hole. However, most physicists agree that any real black hole formed from a collapsing star would not have a stable, traversable wormhole structure, and any attempt to pass through would almost certainly still result in destruction at the singularity rather than a scenic trip to another universe. Falling into a black hole in real life, therefore, would almost certainly be a one-way trip toward destruction rather than a doorway to somewhere else. Beyond the physics of your own fall, it is worth considering how a black hole would affect anything nearby before you even got close to the event horizon. Many black holes, especially the supermassive ones at the centers of galaxies, are surrounded by a swirling accretion disk made of gas and dust that has been pulled in by gravity but has not yet fallen past the horizon. As this material spirals inward, friction and compression heat it to extreme temperatures, causing it to glow brightly across the electromagnetic spectrum, sometimes making these regions among the brightest objects in the entire universe, easily outshining every star in their host galaxy combined. If you were approaching a black hole with an active accretion disk, you would likely be bombarded with intense radiation long before you ever reached the event horizon itself, meaning in many real-world scenarios, you might not survive long enough to experience spaghettification or time dilation at all. There is also the strange theoretical possibility raised by some physicists that information falling into a black hole is never truly destroyed, but instead gets scrambled and eventually released back into the universe over unimaginably long timescales as the black hole slowly evaporates through a process known as Hawking radiation. This idea suggests that every black hole, no matter how massive, is very slowly losing energy and mass over time, and given enough time, potentially longer than the current age of the universe itself, even a supermassive black hole would eventually evaporate completely. If this theory holds true, then in some strange, deeply theoretical sense, the information that made up you and everything you experienced during your fall might not be lost forever, but instead reappear in some scrambled, unrecognizable form billions or trillions of years in the future. Falling into a black hole is one of the only scenarios in modern physics where your own personal experience and the outside universe's experience of the very same event would look completely different from one another, where gravity is strong enough to warp the flow of time itself, and where the fundamental rules of physics break down entirely at the very last moment. It remains one of the most extreme, most mysterious, and most genuinely unknown experiences that could ever happen to a human being, sitting right at the exact edge of everything modern science currently understands about reality itself.